Welcome to our latest video on segment routing innovations. Today, we will focus on iOS XR release 7.3.1. My name is Jose Liste, DTME at Cisco. This video will focus on segment routing MPLS innovations, and its content will be broken into 4 major topics: IGPs, performance monitoring, traffic engineering, and lastly, multicast. Let's get started with segment routing innovations for IGPs. iOS XR release 7.3.1 brings a lot of new functionality for OSPF as well as ISIS. Our first feature will be support for LFA, loop-free alternate, or topology-independent LFA for FlexAlgo with OSPF. This new feature brings the value of TI-LFA and LFA to segment routing FlexAlgo when using OSPF. As you will know, FlexAlgo is one of the key building blocks for segment routing traffic engineering, and now with OSPF, we can also benefit from having TI-LFA. Well, TI-LFA will provide you automated, topology-independent, sub-50 millisecond protection per prefix that is now optimized for a given FlexAlgo. Well, as you know, every FlexAlgo instance will run its shortest path computation for the primary, and now for OSPF as well as for the backup. And we call the FlexAlgo topology of algorithm K, we call it topology K. With this feature, now the TI-LFA algorithm will be able to run for OSPF for the FlexAlgo topology of topology K, where the backup path will be expressed using prefixes belonging to algo K. As a result, the backup path that is computed by OSPF will now be optimized for a FlexAlgo. Let's look at an example. All the routers are members of a FlexAlgo instance called 128. In this instance, we are minimizing the IGP metric while avoiding traversing the link with the red affinity between nodes 3 and 5. We will consider the case where router number 1 is the point of local repair, where we program primary and backup paths, and we're going to use destination of the loopback of router 3 in this example. Router 3, as shown, will have 2 segment routing labels associated with its prefix. A blue label, 16003, belonging to Algo 0, and a violet label, 16803, belonging to FlexAlgo 128C. Well, both the primary paths for Algo 0 as well as Algo 128 will go via node 2 and then onto the destination node 3. You can begin to see as well there are going to be backup paths computing independently for Algo 0 and Algo 128. And you will notice that the backup path is encoded using the labels corresponding to Algo 0. Well, it means that when the link between 1 and 2 fails, the traffic enforcing the backup path for algorithm 0 is going to go via node 6 through a high metric link between 6 and 5, so that's this adjacency seed, and then it will follow the shortest path from 5 to 3 based on the fact that it's going to use the prefix seed of node 3. That will mean that this traffic for Algo 0 will traverse the red link. On the other hand, the backup path for FlexAlgo 128 is also going to go out via interface 6, jump onto node 5, but then is going to follow the shortest path using the Algo 128 label of node 3, which means that I am going to go via 4 and onto 3 and avoiding traversing the red link. So as you can see, the backup path for the destination 3 on FlexAlgo 128, as it is the case for the primary, also avoids the red link in the backup. With this release, we bring comprehensive TI-LFA protection for FlexAlgo using link protection, node protection, local SRLG, and weighted remote SRLG for OSPF in 7.3.1. For those of you who are running ISIS, the support for ISIS with LFA and TI-LFA protection with FlexAlgo was already shipping before 7.3.1. So the support was already there. Now, to demonstrate this concept, why don't we jump into a topology? And we're going to see the concept in action. First of all, these routers are part of a topology that is running a FlexAlgo instance that is minimizing the delay. So the metric type of the FlexAlgo is delay. With 7.3.1, we can now observe the OSPF route for a FlexAlgo 128 and one of the prefixes, 1.1.2. In this case, it's a loopback of router number 2, and we're going to be asking also for the information for the backup path. So as we can see here, we can see the prefix on the primary path with a metric, with a particular label that will be imposed if we're going to that router, and we have my particular interface 2002 as my primary. In addition, with the support of TI-LFA, we can observe that we have a backup path. It's a TI-LFA backup path where we're going to use node router number 4, 1.1.4, as my repair in my repair list. So this is my P router, my PQ node router in particular, where I'm going to be imposing the label of that device, 17804. And this is the segment routing label for FlexAlgo 128 on node 4. The backup path will be enforced leaving the router on interface gigi 000, and I do have a metric cumulative delay of 34 when using the backup path. By default, in 731, every FlexAlgo will have a LFA and TI-LFA enabled, and here's where you can see the backup path. We do have the ability to disable it on a FlexAlgo level. So let me show you a case where I'm going to disable FlexAlgo, disable TI-LFA for FlexAlgo 128. So this is my configuration to achieve that. Let's commit the config and come back to the exec prompt. And when we inspect again the same prefix 1.1.2 for FlexAlgo 128 and looking for the backup paths to be displayed, we can see that there is no longer a backup path. I only have my primary path going via 000. Moving along, we go to our second OSPF feature in iOS XR 731. We call it the rounding of mean delay values. The objective of this feature is to allow the IGP to normalize the measured latency before it is advertised by the IGP. So consider the picture on the right-hand side where all the numbers on the links represent the measured delay for a particular link between two nodes. And in particular, we're going to focus on the delays for the links between 5 and 6 and 1 and 3. We can observe that the minimum delay path from 0 to 9 is via node 5 and then on to node 6. That will give me the minimum delay, the absolute minimum delay between these two nodes. However, if I were to go via 1 and then 2 and 9, I know that my delay will only be increased by 2 milliseconds, considering the difference on the delay between 1 and 2 and 5 and 6. The idea behind this feature is to allow customers to provide paths that minimize latency in the network at the same time that maintain ECMP properties when the delay difference is insignificant. So now, if these delays were to be normalized, in this case we show a normalization proposal of equal to 33. Now, for node number 0 to go to number 9, minimizing delay, he will actually use both ECMP paths via node 1 and via node 5. With the similar topology, the idea is to provide the low latency service. We know that we want to avoid links with high latency. In this particular case, the crisscross links are the links that have high latency, but the remaining links are all pretty low latency as far as we're concerned. And the latency is very hard that it will be identical, but it is low enough that I would like to normalize. So the idea here, as I mentioned before, is to be able to normalize the latency on those links that surely have a very low latency. So if I take a look at the links from 1 to 2 or from 5 to 6, I would like to be able to configure OSPF to normalize the delay before it is advertised in the IGP. Now, it's important to remember the measurement of the latency on the link is being done by performance monitoring, which is another building block in iOS XR. And that performance monitoring process will give the delay to the IGP. And here, with this feature, before the IGP will simply propagate that value in its flooding, it will actually normalize it before doing that. So what you can see in the configuration is that we have a new feature that you configure under the interface on your area for OSPF or under your ISIS interfaces. You will configure the delay normalization feature by using two parameters. One is the interval size, the other one is a given offset. In these particular pictures in the bottom, we demonstrate how the interval and the offset play together so that a delay normalized d sub n will be arrived. So in this case, the sample with the delay measure of 31 will actually belong or be normalized to the beginning of the interval from 33 to 43. In the case of the sample, the delay measure 29, it will be normalized to the end of the interval that ends on 33. So therefore, with this configuration, both samples at 31 and 29 will be normalized to delay value of 33. This delay normalization is new for OSPF in iOS XR 7.3.1. For those of you who are using ISIS, this functionality was available before this release and is already shipping. Let's jump into my lab and let's take a look at this feature in action. So here we have an interface, Gigabit Ethernet 0.0.0.2, where we have a measure delay of 11 milliseconds. This is the performance monitoring module that I mentioned earlier that is going to measure the delay on a given link between two nodes. And if we take a look now at OSPF, the OSPF database, we look at the LSAs that are going to advertise or describe this link between router 1 and router 2. We will see here that we include the information for the unidirectional link delay, the minimum, the maximum, the average, and the jitter. So in this case, before the feature is configured, we can see that the measure value is going to make it into the flooding through the LSA flooding in the OSPF database. No differences there. But now we're going to go into the router and we're going to configure the delay normalization feature. So under OSPF area 0, interface Gigi 0002, I'm going to configure my delay normalization interval 10, offset of 3. Commit the change, get out, and take a look at the OSPF database again. And we can see now that the value that will be advertised in OSPF database is now the value of 13. My minimum delay has been normalized, in particular for the use of the routing protocol, or anybody in the IGP domain was normalized from 11 to 13. The idea behind this feature is to provide the operator the ability to control the conditions that will lead to the advertisement of a prefix associated with the loopback interface. The conditions will be given to the operator, such as monitoring reachability to other prefixes in the network. Hence the name Conditional Prefix Advertisement. Now, one of the leading use cases for this feature, when applied to segment routing, is, for example, as shown in the picture, having the ability to define a segment routing policy from, let's say, node 1 to node 4, where one of the segments, the first segment in this policy, is the prefix seed of a Anycast prefix between routers 2 and 3. So there is an Anycast group for the prefix 1.1.1.100 with a common segment routing prefix seed, 16,100. This is going to allow the operator to have a highly resilient segment routing policy with load balancing that goes from 1 to 4. But if the conditions are not correct for node number 2, we want to avoid sending traffic to node 2 that could lead to a temporary blackholing or to suboptimal routing. So what we are looking for is the ability for the routers, like nodes 2 and 3, to be able to track connectivity or reachability towards domain 2. And if that connectivity is not there, for example, when the link between node 2 and node 4 goes down, then we would like to automatically make node 2 stop advertising that Anycast address. What you will see from the configuration is that you will configure a prefix set where you will include a number of prefixes that you would like the router to monitor connectivity to. This prefix set is going to be referenced on an RPL. The RPL will have a if statement with the well-known rib has route that is going to be referencing the prefix set from the previous step. You will notice that we have added a new semantics to the rib has route if statement, which is now the async clause. And this is very important because it will allow the clients to be notified based on event driven. There are no timers where the clients are just going after rib. No, automatically when the conditions fail, the client will be automatically event-driven, non-notified. And this RPL is going to be configured under OSPF, under the area, under the interface loopback that we would like to have the conditional advertisement. When the router loses reachability to all the prefixes in the prefix set, OSPF, in this case, will stop advertising the prefix associated with this loopback. This feature is not only applicable to segment routing environments, but it is in general applicable to the advertisement of prefixes. On the left-hand side, you have an example where the reachability conditions are met, and you can see the output of the show OSPF interface for the loopback that it has a conditional advertisement RPL. We can see that the policy results are passed, therefore the prefix is advertised. On the right-hand side, the conditions fail, and at the outcome, the prefix will not be advertised. Like in the other features that you have seen, this functionality, which is introduced for OSPF in 7.3.1, is already shipping for ISIS for those of you who use ISIS as your IGP. Let's see this in a demonstration. Okay, now let's jump back into my test bed. Now we're going to go into my router number 2, where we're going to demonstrate this new feature. So we are going to take a look first at the configuration. Identically, as you saw in the slides, we have an advertised prefix CLI under the loopback number 1. This is a Anycast loopback between router 2 and another router in the topology, router 3, where we're going to reference a policy, an RPL that is called track domain 2. This RPL is going to be referencing a prefix set called domain 2, where I put the IP address of one of my local interfaces, and that prefix set is referenced in the RPL policy track domain 2 that was referenced earlier here. And you can see the if rib has route clause with the new async, and then the prefix set name. Well, here we go and look at OSPF interface output for the loopback number 1. We can now see the IP address of that prefix of that loopback, which is 1.1.1.90. We can see that now we are passing the verifications for the IP addresses in the prefix set, and therefore the prefix is being advertised. If we look at the OSPF database, because I want you to see the difference, we can see that my router link states my LSAs are describing 9 links. So at this point, everything is up. And if we look inside of the OSPF database at my router link states, I'm looking for the prefix 1.1.90 in the database, and I find it. So I know that it's being advertised, and I found it in the database. So now we're going to go and we're going to shut down the link that is connecting me to the domain number 2, and that link has the IP address that I'm tracking, okay? So I'm going to shut down the interface geeky 0001. We're going to commit. We're going to exit. We're going to come back. We can now see that my OSPF interface for loopback 1, my conditions are not met. So the RPL is leading to the drop policy result, and this prefix is not being advertised in the domain. To prove it, we can look at the OSPF database, and we can see how the number of links described by this node has been reduced from 9 to 6. So there are 3 links less. One of them is the loopback. The other one is the link being shut down, the host route, and the subnet route associated with that link. So there are 3 links less that are advertised in that device. And if we try to locate the prefix 1.1.90 in the database, this prefix is no longer advertised. Well, now we're going to move on to new innovations in iOS XR 7.3.1 for ISIS. And the first one is the what we call TI-LFA protection for unlabeled IPv6 prefixes. With this new feature, we are expanding the coverage of TI-LFA to also include IPv6 prefixes which have no prefix seed. Obviously, you will understand the ability of TI-LFA to support or provide protection for IPv4 or IPv6 prefixes that have a prefix seed, and now we are augmenting it here in 731 to also protect prefixes that do not have a prefix seed. So if you look at the topology on the right hand side, we have some destinations like Z that are IPv6 addresses advertised in ISIS v6 that do not have a prefix seed, so they're not coming from a segment routing enabled route. But the routers below, from 1 through 5, are segment routing enabled. In this case, we would like to look at the programming on router number 1 for protecting traffic going to Z. The primary interface to go to Z will be via the interface to 2. But with this new feature, and if this interface between 1 and 2 goes down, router number 1 will install a backup path where we're going to send the traffic to router number 4. So 4 will be acting as my PQ node, and then we're going to release the traffic from 4 onto the destination Z, following the shortest path. We expand the value of TI-LFA to also cover traffic or destinations in the IGP that are not labeled, that do not have a prefix seed. And this is actually common in many cases where I may have a network that is running MPLS, and some of the traffic is actually carried as pure IP, therefore being unlabeled. With this new feature in iOS XR 731, all the IPv6 prefixes without a prefix seed by default will be eligible for TI-LFA backup path computation. We do have knobs that the user can configure to disable this functionality, so we do not compute backup path for any unlabeled IPv6 prefix, or we can have the granularity knobs where you can configure prefix lists or route policies where you can actually control which subset of unlabeled IPv6 prefixes are going to be eligible for a TI-LFA backup path computation. We do recommend the ability or the use of these more granular statements, because then you can protect what's important, and therefore you're going to preserve resources only for those prefixes that really you care about. So if you look at our comprehensive support for TI-LFA, there are many types of traffic types that can be protected. Obviously, segment routing label traffic, so the prefix are label prefixes advertised in ISIS or OSPF. Almost from day one, we had support to protect IPv4 unlabeled traffic, and that is shipping for ISIS and OSPF v2. And what we're introducing on 731 is IPv6 unlabeled traffic with ISIS. Obviously, this is not applicable for OSPF v2, as OSPF v2 only supports IPv4 routing. Okay, so we're back on router number 1, where we're going to demonstrate the ability of ISIS to compute a TI-LFA backup path for an IPv6 unlabeled prefix. So in this particular router number 1, with iOS XR 731, we can find a destination 2001:2222/128. That the destination will have a primary path leaving this router via gig 002, and it will have a backup path. In this case, this backup path will be link protected. It's going to take me via gig 000. It's going to have a repair path list using a PQ node of router number 4, for which we're going to be imposing the label 18004 if I want to protect traffic to that prefix. This label 18004 corresponds to the prefix seed of router number 4, which is 2001:111:4. And you can see, as evidence of this feature, is that the prefix that we are protecting has no label. So in this case, the backup path will be pre-computed. In the backup path, we're going to push the label of the PQ node, and then once the traffic gets to the PQ node, it will continue going along the shortest path without any further labels, so it will be unlabeled traffic after hitting the PQ node. Well, to demonstrate the granularity that we have, we're going to basically disable it for all the prefixes. If you remember, I mentioned we do have the ability to disable the pre-computation of a TI-LFA backup path for all the prefixes, which is what I'm doing here, or also based on a selective knob using prefix sets of RPL. So in this case, we're going to commit. We're going to disable it for all the prefixes. So we committed that change through this Segment Routing MPLS on-label protection disabled. And then we come back and we look at the ISIS table for that prefix. And now the prefix that we explored a moment ago has no FRR backups. Okay, now on to our last ISIS feature in iOS XR 7.3.1. It is the what we call inter-level SRMS advertisement propagation. For those of you who recall the important role of the SRMS, the SR mapping server is used for cases where we need to do interworking between SR and LDP, label distribution protocols. The SR mapping server is a control function that advertises segment routing labels for LDP-only destinations. It is a function that lives in the control plane. It advertises that mapping from a prefix to a segment routing label. What we're doing now is we are actually facilitating the deployment of the SRMS such that the SRMS can be located in one level. So on the picture on the right-hand side, the router number 6 is acting as SRMS, and the advertisements coming out of node 6 will be able to be propagated towards the level number 1 on the right-hand side via the L1, L2 routers, router number 2, and router number 5. The value of this feature is that it allows me to simplify and reduce the number of SRMS nodes that I need to have now, thanks to the propagation of these advertisements between levels. ISIS implementation supports the SRMS function since day 1, and these mappings were advertised in all levels or area on an L1, L2 ISIS router. Before 7.3.1, these advertisements were not propagated between levels. Therefore, unless the mapping server was sitting on an L1, L2 router and you had a contiguous backbone of L1 and L2 routers, a mapping server used to be required for each ISIS area. With iOS XR 7.3.1, you will be exposed to a new configurable knob. In this case, we can see it here in blue. The knob called domain wide under your segment routing prefix seed map configuration that will allow this SRMS to instruct all of these L1, L2 routers to propagate the SRMS advertisements from one level to another. We do like to expose you to our comprehensive functionality, not only in ISIS. In ISIS, this is brand new in 7.3.1. In the case of our OSPF implementation, the propagation of SRMS advertisements inter-area has been shipping for quite a while, so it's already a shipping function. And with this, we end our summary of segment routing innovations for IGPs in iOS XR 7.3.1, and we're going to be now moving on to our next topic, which is going to cover the segment routing MPLS innovations for performance monitoring.